All right, welcome back, everybody. This is our third day thinking about Taylor series and playing around with them. Last time, we got to think about sine of x and cosine of x, and we used the definition of Taylor series to compute those. Right, we just cranked out a bunch of derivatives and then found the pattern and used that to write up these nice standard forms for these power series. Right, and over here on the right, we have our expanded forms written out. Notice, so sine of x uses the odd powers of x, and cosine uses the evens, which is kind of interesting. I don't know if we mentioned it explicitly last time, but both of these power series are good for all x. The radius of convergence for these power series is infinity. We can plug in any x here, and it's going to give us what sine of x or cosine of x is. Another thing to note about these two power series is that they're both centered at 0. We can see that just by looking at here, the x term. There's nothing else with the x here. It's not like x minus 3 or x plus 1 or something like that. It's just x. So we can think of that as x minus 0 if we want. So both of these are centered at 0, and that's mostly been the case for all the power series that we've looked at for the most part. But today, I want to look at computing a Taylor series with a center that's something else, something other than just center 0. And then we'll look at finding its radius of convergence. But to start, let's look back at e to the x. Right? And this is a function that we found its Taylor series centered at 0. Remember that we call such a thing a Maclaurin series. And let's use that as kind of a, I don't know, as somewhere to bounce off of in terms of what it looks like to have a Taylor series with a different center. And so we've seen this picture before. Maybe not, actually. I think I didn't show it last time. So you maybe saw it for like 2 seconds as I switched to the other one. Anyways, here is e to the x in black, and here I've kind of punched in a kind of general form for the Taylor series. And so a here, that's our center. It's centered at 0. And if I drag this m, that's going to be giving us more and more terms in our polynomial. And so if we drag that up, and we see these, partial sums polynomials are doing a better and better job hugging our curve of e to the x further and further out. Right? And that's the picture that we've seen before for other functions as well. And so now I'm going to take this center and drag it over to be centered at 1. And before I do that, just take a moment and imagine what you think is going to happen to this picture if we change that center to be 1. All right, let's see what happens. Take that, drag it on over. And as we do that, oops, a little bit too far. There we go. We can see that kind of this anchor point on our curve, that moved over to the x value 1. And so we got this kind of new point that anchors us on to our original function's graph. And as we drag the slider over and get more and more terms, you can see that it's from there now that our polynomials are going to be spreading out and doing a better and better job of approximating our function. And that's really the idea to have in mind with what the center does, is it gives us this anchor point that we then spread out from. So for example, if we take this and move to something else, like -3 or something like that, then again, we'll just have a different anchor point. And if we include more and more terms, they'll spread out from there. Whee! All right. So that's the picture. What it looks like to have our Taylor series centered at something just other than 0. It really just gives us our anchor point here. And so what I'd like to do is kind of do an example where we compute one of these. So we scroll down in the notes. We're going to look at finding the Taylor series for natural log, where the center is a equals 6. Once we do that, then we'll think about finding its radius of convergence. I'm just going to give us a little bit of a start before I send you off to kind of do some work on your own. So if we scroll down here, and we already know what the form of our Taylor series is, right? This is what all Taylor series look like. This is our general formula. And one of the things that we've talked about before is that to fill this in, we really just need to figure out this piece, right? We need to know the derivatives of our function evaluated at our center. Right? Once we have that pattern, we can kind of plug it in right there. And so this is where we just start taking derivatives and plug in our center and see what we get. And so why don't you take a couple minutes and start on that process and see how far you can get in terms of finding the Taylor series for natural log centered at 6. All right, so let's talk about this, and just in case you haven't yet, so if you're working on it, pause the video until you're ready to continue in the notes. But if you're ready, here we go. If we scroll down a little bit, right, we just want to take a whole bunch of derivatives. And so the 0th derivative is just our function. Plug in our center, get natural log of 6. If we take the derivative, we're going to get 1 over x. Plug in 6, get 1 over 6. And I'll just bring up the rest of them. And so here, second derivative, you get negative 1 over x squared. And what's going on there, right? 1 over x, we can think of as x to the minus 1. So take the derivative, the minus 1 comes down and gets dropped by 1. So minus 1 is negative 2. So that's where that second power down the bottom is coming from. Maybe let's just talk about the derivatives. So this is minus x to the minus 2. If we take the derivative there, we get that another negative, which cancels out the one we had. 2 over x cubed. Take another derivative, we get negative 2 times 3 over x to the 4th. And then one more fifth derivative there. 2 times 3 times 4 over x to the 5th. And if we plug in our center 6, here's what we get. And notice I haven't simplified anything. I haven't even computed 6 squared as 36, and I would encourage you to do that as well. It helps to see the patterns that are involved if we don't simplify these. If we just leave 2 times 3 as 2 times 3, if we just leave 6 to the 5th as 6 to the 5th, we're going to be able to see what's happening a little bit more clearly. And in fact, here we can kind of see what's going on, right? We have this alternation going on, positive, negative, positive, negative, positive. Up top in the numerator, kind of building up a factorial. And down on the bottom, we just have this increasing power of 6, right? And so we can start looking to capture this pattern here, right? So we're going to have some of this fraction, we're going to have an alternation, and we just need to choose the power so that it matches. And so, right, if we just start with a guess of, oh, I don't know, maybe it's like to the nth, well then, if we come up here with n equals 1, that would be the first derivative, we would get minus 1 to the 1, which is minus 1, but we actually want a positive here. And so we're going to have to adjust that just by 1, and so we can just do n plus 1 or n minus 1, it doesn't matter. That'll give us the right sign, positive or negative, at these different levels. Next we talked about, we saw that we had a factorial that we were building up. And so we just need to kind of connect that to the index that we're looking at, what derivative we're looking at. And so here 2 is 2 factorial. We saw that when we're taking the third derivative. For the fourth, we have 3 factorial. For the fifth, we have 4 factorial. And it looks like we're just 1 behind, right? So for the nth derivative, what we'll have over here is just n minus 1 factorial. And then in the denominator, we just have this increasing power of 6. And let's just look at the different derivatives. Second derivative, we see the second power. Third derivative, we see the third power. Fourth, we see the fourth. And so it's just matching the power. So the nth derivative is going to have 6 to the n in the denominator. And so right there, that's our nice general formula for what we were needing to find, right? The nth derivative of our function evaluated at 6. And so that's going to be what we plug in right here. The only issue is that this pattern, right, for the nth derivative, given the factorial up top and a power of 6 on the bottom, that actually is not the pattern for the very first term, right, or the 0th derivative. And so since this is only the pattern for n bigger than or equal to 1, right, so for these terms and continuing forevermore, what we need to do is essentially just take this sort of, I don't know, this oddball here, the 0th term, and we'll just kind of let that hang out by itself, and then we can capture the rest of this in our summation notation. So what that looks like is like this. So here we've popped off that 0th term, which always is just our function evaluated at our center, and then plus we have the sum starting from n equals 1, right? Because over here, this was our n equals 0th term. So we've separated that, and so our series is going to start at n equals 1. And up top, we just have our formula that we found plopped in where it goes. Up in the numerator, take that, right? Taylor series formula says to take that, divide it by n factorial, and then over on the side, we still have our x minus 6 to the n. All right, and so with that, we have successfully computed the Taylor series for our function, natural log of x centered at 6. But we're still in the middle of this example, right? We also, just scrolling back up, we wanted to find this thing's radius of convergence. And so how we've done that for most of our power series is using the ratio test, right? And so looking at this thing, that sounds unpleasant, at least right now. We got 2 factorials going on, and so what we'd like to do first is to take this and simplify before we try and do any sort of ratio test on this thing. So that's one of the things that we're going to do. The second thing is you might very naturally be wondering, well, what about this natural log of 6 off on the side? How does that play into the radius of convergence? And the answer is that it actually doesn't at all. We can actually completely ignore that first term, just pretend like it isn't there. Essentially, the idea here is that just ignoring a single term, that won't affect whether or not the series converges. It'll affect what it converges to, right? We'd be off by natural log of 6, but if the series converged before, then if we take out the natural log of 6, it's still going to converge, and vice versa. And so in terms of finding the radius of convergence, we can just ignore that and just focus in on our summation notation portion over here for the n equals 1 up through the rest of the terms. And the second thing, as we were talking about, we definitely want to simplify this thing as much as we can before we do the ratio test. And so what we're going to do there is essentially we're going to have, we have fractions upon fractions, so let's work with that a little bit first. All right, we have minus 1 to the n plus 1, and then n minus 1 factorial. And here, if we take this n factorial and think of that as n factorial over 1, and we flip this bottom fraction and multiply, the n factorial is going to cozy up right next to the 6 to the n. And notice what's going to happen here, this thing that we've seen before, this n factorial on the bottom with the n minus 1 factorial up top. And that's going to nicely simplify n factorial. We can write as n times 1 down from that factorial, and so our n minus 1 factorials will just cancel, and we're left with just an n in the denominator, which is much nicer to look at. And so here's what we get when we've done that simplification. And so it's this summation that we're going to use to help us with the ratio test. And so in terms of the ratio test, right, we're looking at the absolute value of the ratio of successive terms. And so it's this stuff that we're adding up, right? This is our AN for the purpose of the ratio test. And so it's going to take a little bit of work, a little bit of writing to figure out this thing's limit, but we can do it. Why don't you take a couple minutes now, pause the video, and see if you can work out this limit, and then see what the ratio test then will tell us about the radius of convergence for our power series here. All right, well, let's start in. So here, on the left, I've written our AN plus 1. And so again, the idea here is to, wherever we see an n in our formula here, we're going to swap it out with n plus 1. So here, with our minus 1 exponent, we'll actually end up with n plus 1 plus 1, so n plus 2. And then 6 to the n plus 1 times n plus 1, and the exponent of n plus 1 on our x minus 6. Then I've just already taken AN, I've flipped it and multiplied, and so that's where this stuff on the right is coming from. All right, so now we just have some simplification to do. All right, we have n, x minus 6 is down here, and n plus 1 up top. And so these are going to cancel out with all of those, and we'll be left with just a single x minus 6 up top. Similarly, we have a pile of n factors of 6 up here. Those will cancel out with n of the factors of 6 down below. The absolute value will actually just eat up our -1 to some powers. We don't even need to worry about simplifying, those. These are both just either +1 or -1, and just they're multiplied, and so the absolute value will just eat those up, and those will just go away because of the absolute value. All right, so what are we left with? When the dust settles, we have an n up top, an n plus 1 on the bottom, a 6 in the bottom, and we have our x minus 6 up top. The n plus 1, and 6 are all positive, The x minus 6, it depends, right? Depends on what x is. We don't know if that's positive or negative, and so we want to leave the absolute values on that, right? And so this is what we get when the dust settles with our simplification. And now we just need to take the limit of this thing, right, as n goes to infinity. All right, and so here, we're imagining that x is some, some constant that we've chosen and plugged in. And so then this absolute value of x minus 6 is some constant, and this 6 in the bottom is. And so we can actually slide this stuff out as a constant multiple. And we can just then take the limit of what's left. And here, we could use L'Hopital's rule, since this is an infinity over infinity limit. And derivative up top is 1, same on the bottom. And so this piece ends up just being the limit of 1, which is 1. And so feeding that back into our main stream of work, right, we just found that the stuff here, that this equals 1. And so if we sub that in, we've now computed our limit. And so this is our L in terms of the ratio test, right? And the ratio test tells us that our series converges if L is less than 1, right? Our L is right here. And so we just want to see what this tells us. Well, if we take this inequality and multiply both sides by 6 to get this absolute value all by itself, then we get the inequality we see here. And what this is telling us kind of geometrically, right? The absolute value is telling us, well, the distance that x can be away from the center of 6 has to be less than 6. And so it's this 6 here that is telling us our radius of convergence. That's how far away from our center that we can be. And so our radius of convergence is 6 for our Taylor series centered at 6. I'd like to, real quick, go back over, and we can actually see this in action. We bring up another Desmos graph. Here is natural log of x, and down here at the bottom, here we have the formula that we figured out for the Taylor series centered at 6. And so if we pop that on, then notice our very first approximation is just the constant natural log of 6, and it is indeed anchored onto our function at x equals 6. And if we slide this slider over, we'll be getting more and more terms, and indeed we're anchored right at x equals 6, and we can see these doing a better and better job of hugging our function. But notice we do have kind of this barrier that's set up, right? Right at around 12, we see this kind of freaking out over here on the right, and that behavior is exactly what it looks like to have a finite radius of convergence, right? We found that the radius of convergence for our power series was 6. And so if our center is at 6, well then if we bump up from that by 6, then yeah, right about 12, we should expect this thing to start deviating and moving away from our function. Over on the left, that radius of 6 brings us all the way down to 0. And so we're just going to be heading on down there. All right, so that's the picture. Again, we're anchored at 6 by our choice of that center of 6. And that's what it looks like to compute the Taylor series for a function where our center is something else besides 0. And then take our formula and find its radius of convergence. As a bonus example, if you're eager for more, we already found our Taylor series for sine of x and cosine of x. We have those formulas here. but we didn't actually go through and find their radius of convergence explicitly. So that's actually something that you can do at this point. Pick your favorite function, sine or cosine, take the formula here and see if you can work through the ratio test and find the radius of convergence. You just got to be careful to deal with the factorials correctly as you're writing down an plus 1 and doing simplifications and whatnot. But yeah, that's definitely an exercise that would be good to work through. I encourage you to do that. That's it for today. If you have any questions on the lecture, post those to Piazza, and I'll see you next time.